So here we are in the last series of videos for the course. I'm going to go through the rest of the functional groups that I haven't discussed so far. Almost all of them contain oxygen. That's why chapter 14 is titled Organic Compounds of Oxygen. But I also would like you to review parts of chapter 15 in the GOB textbook, 15.1 to 15.9 and 15.11 to 15.13 that talk about carboxylic acids, esters, and amines. Now, there's a lot of material in these two chapters. I don't expect you to read it all because there's a lot of stuff about the reactions of these compounds and how they're made, physical properties that I'm not necessarily going to comment on every little thing. You should kind of listen to what the topics I'm talking about here and then just read those particular topics in these chapters. It may or may not be I might be a little bit repetitive with what the book said. There are only so many examples you can give on these topics without getting too complicated. But I'm just going to kind of go through all the functional groups, talk to you about some of the properties of them, and how to name them. That'll be a big part of next week's quiz, how to name a variety of different compounds, and maybe some questions about some basic, very basic reactions. I'll specify when I'm expecting you to concentrate on that. Especially the synthesis of esters is a very important reaction. And the last topic I'll talk about is amines, which are nitrogen-containing compounds. So again, this is just a overview of everything. This what I'm talking about in these next 5 or so videos is normally covered in a semester or two of a course. So it's going to be very sort of, just glossing over a lot of the topics. So this is a chart you'll see here in chapter 14. Kind of goes over all the different functional groups. You should recognize the different connections, how the endings of the names of the compounds that I'll go over. For instance, we've already talked about alkanes, alkenes, and alkynes. They end in ane, ene, or yne. Today I'm going to talk about alcohols, ethers, aldehydes, ketones, carboxylic acids, and esters, which aren't on this chart, and actually amines as well. So for the next week or so, get through these videos, and the last quiz that you'll have next week will be on this series of videos. So a lot of the good news is a lot of the rules that you learned for naming alkanes, alkenes, and alkynes applies to the rest of the compounds. This is very logical stuff. You learn a few basic rules. You can apply these naming rules to almost every class of compound. What you should recognize in these compounds like aldehydes, ketones, and carboxylic acids and esters is they all have something in common. They have this very familiar functional group called a carbonyl group. It's spelled C-A-R-B-O-N-Y-L. I'll talk a lot about that tonight in these videos. And you should recognize the specific group here is called the functional group. You can instantly look at a molecule and tell what kind of compound it is. And an experienced chemist would know the reactions these would go under, the boiling points, the melting points, all that sort of thing. It's a continuation of this language. But organic chemistry is extremely useful in many areas. Doctors and biochemists, they all have to take organic chemistry at some point just to learn how molecules that are the building blocks of life work. A lot of these compounds are polar because they have this carbonyl group. The carbonyl group is polarized delta plus and delta minus. That means that since oxygen is more electronegative than carbon, the oxygen has a slight negative charge with this delta negative, and the carbon has a slight positive charge with this delta plus. That has a lot. That says a lot about or influences a lot of the what am I trying to say? It causes a lot of interesting things to happen. Since these are polar, a lot of these compounds are water soluble, not all of them. The smaller versions of these, if they're between 1 and 5 carbons long, they're generally water soluble because they can hydrogen bond to water because this oxygen can hydrogen bond to a hydrogen of water. But a lot of them don't have the ability to hydrogen bond with themselves. Some of them do, like carboxylic acids can hydrogen bond to themselves, and so can alcohols because they both have this OH group in them, and that's the criteria for being able to hydrogen bond with yourself. so that you have alcohols and carboxylic acids tend to have higher boiling points related to the other compounds. Aldehydes don't have the ability to hydrogen bond, so they're more volatile, and so are esters. They don't have the hydrogen here. They have another carbon group substituted. So esters are kind of a derivative of a carboxylic acid. You take a carboxylic acid and you replace the hydrogen with a carbon group. Notice I've used this R or R prime. That just represents some group of carbons. It could be a methyl, an ethyl, a propyl. It's just a generic term for carbon. But anyway, esters, since they don't have that ability, are more volatile. That's why esters and aldehydes, being more volatile, are they generally smell better than other classes of compounds. They're used in perfumes and fragrances and artificial flavorings and things like that. So let's get started with more specifics. I'm going to go through alcohols first, some physical properties of alcohols. The general formula of an alcohol is ROH. So you've seen a lot of alcohols in this course. I've built some molecular models in 3 dimensions. This is what, I don't know if it comes across in the camera, but this is a molecular model of ethanol, otherwise known as ethyl alcohol. It has the OH group here, and it's got a CH3CH2. But so you can see these are 3-dimensional molecules. They kind of make a zigzag pattern. That's what you've been seeing me draw a lot in these videos. That zigzag pattern that you see as carbon chains get longer and longer is a result of the tetrahedral nature of carbon. So that is ethanol. I'll show you some molecular models of all the different types of compounds I'm discussing. But alcohols can either be primary, secondary, they can be tertiary. What do I mean by that? I mean that they can either have the OH attached to one carbon, they can have the OH attached to a carbon that has 2 carbons attached to it, or they can be attached, the OH can be attached to a carbon that has 3 carbons attached to it. So each of these types of alcohols exists. Ethanol would be an example of a primary alcohol. The OH is on the end of the chain. And naming them is pretty standard. I'll go through naming those. So the names I'm not going to necessarily comment as you see them here in the videos. This is isopropyl alcohol, which is the same 70% solution of this in water is rubbing alcohol. And you'll notice this is a secondary alcohol because the OH is attached to a carbon that has 2 carbons attached to it. So these are ways we classify organic compounds. There's also aromatic alcohols. This is phenol. This is also known as hydroxybenzene. Again, don't worry about learning the names right now. We'll get to that in time. This is an aromatic alcohol, obviously, because it has the benzene. This has a very different chemistry than these because it has the presence of the benzene ring. Phenol is used as an antiseptic. You've probably used it in sore throat medications. They use it in cough drops, all sorts of stuff. It is somewhat toxic because of the presence of the phenol. But you should be able to recognize primary, secondary, and tertiary alcohols. Don't worry so much about memorizing boiling points and melting points of these things. Just recognize that you are looking at an alcohol, what type it is, and how to draw the structure. Some of the important physical properties of alcohols are that they generally have higher melting and boiling points relative to hydrocarbons, and I think this meant to say ethers of the same size. That's a typo. That's supposed to say they have the same boiling point of hydrocarbons, alkanes, and ethers of the same size. They have higher water solubility relative to hydrocarbons and ethers of the same size. I'll go through and show you what I mean with that. Alcohols, since they have the ability to hydrogen bond with water and with themselves, they have very high boiling points. The boiling point of ethanol, I think, is somewhere in the 70-degree range. That's pretty high for a molecule that's kind of small that only has 2 carbons. So ethanol is also very water soluble because the old adage like dissolves like is applicable here too. You have the oxygen of the ethanol, hydrogen bonding to a hydrogen of a water molecule, so ethanol easily dissolves and is miscible with water, and also strongly bonds or hydrogen bonds to itself, so it generally has a higher boiling point. Comparing just some molecules of similar size, propane, this is called dimethyl ether, and this is ethanol. They all are about the same size molecule. But this is a gas at room temperature, this is a gas at room temperature, and this is a liquid at room temperature, like I said, because the intermolecular forces between ethanol molecules is so much larger. Dimethyl ether and propane cannot do this. They can't be attracted to water or themselves with hydrogen bonding. These just have dispersion forces. This has a slight dipole-dipole force with itself, but that's nearly not as strong as that's not nearly as strong as a hydrogen bond. So therefore, dimethyl ether and ethanol have similar. Well, for the reason that these have oxygens, or the fact that they do have oxygens, means that ethers and alcohols will be soluble in water relative to alkanes, which are not soluble in water because these don't have an oxygen. So this is what you should kind of pick up on in this course, is how do you, you can look at a molecule, pick up on some specific atoms, polar bonds, electronegative atoms like oxygen, and make some deductions like they have a slight water solubility because of that. And so to make predictions like that is a useful skill to take out of a class like this. Let's just compare some of the melting points and boiling points of these compounds to show you a little bit more what I mean. These are all molecules that kind of have the same size and molecular weight. So they're all in each row, each series of 3 compounds has about the same molecular weight, within about 2 grams per mole of each other. So propane, dimethyl ether, and ethanol, you can see the trend and the upward trend in boiling points. All can hydrogen bond to itself, so they have much higher boiling points than the correspondingly sized ether or alkane. Notice that the boiling points of all these substances generally goes up within the group as you get larger and larger. That's because as the molecules get larger and larger, as I've said many times, the dispersion forces and the dipole-dipole forces get stronger and stronger as the either the polar molecules get larger, the dispersion forces get larger and larger here, so these molecules are more attracted to each other than these, so the boiling point goes up. This also applies to the melting points. It's just easier to talk about boiling points, I think, because liquids to gases is something that it's just easy to understand. But if you go down to like propane, for instance, at some point the alkanes and the ethers generally have the same same boiling point for similarly sized molecules. So eventually the oxygen of the ethers does not have the effect that it did when they were smaller. It makes the molecule behave somewhat like a more nonpolar molecule, because boiling point is a reflection of how strongly the molecules are attracted to themselves, because you're taking a liquid and converting it into a gas at these temperatures. So you have to pull the molecules apart from the liquid to the gas state. But alkanes and ethers with similar molar mass have similar boiling points. Alcohols, because they can hydrogen bond, as I've said, have much, much higher boiling points than the corresponding size molecules that are ethers or alkanes. It's a lot of words you're digesting here, so again, take your time going through these videos. I'm kind of going quickly through some of this stuff, and I'll slow down when we get to the naming. Okay, so let's move on. I think you saw everything you need to see from that slide. I was just trying to get across the point of intermolecular force trends and things like that. Let's talk about naming alcohols. Again, on your quiz next week, this will be one of the primary focuses of testing you, because since we're not meeting in person, I can't go through reactions, we can't do lab work. So this is one of the few things I can teach you in a video such this is how to name these compounds. The rules are very similar, as I said, to naming alkanes. You generally go to naming any compound, whatever functional group it has, you go to the parent alkane. That's why I wanted you to memorize methane, ethane, propane, butane, pentane, etc., because those names, those prefixes are going to come up. This part of the name will come up a lot. Methane, prop, prop, butane, whatever. Those parts of the words are repeated. So for a methanol, the simplest alcohol, what does that look like? It's a pretty simple molecule. I thought I built one of those. Where is it? Well, I showed you ethanol. I guess you already saw an alcohol. But they all have the OH group, and you have to give the position of the OH as the chain gets longer. But for methanol and ethanol, you don't have to. It's either, the only place it could be is here on that carbon, and the only place it could be in ethanol is here. If it were here, it's the same molecule. So there's no number needed. And a lot of these names I'm going through in these classes of compounds are what are called common names. There's a group of there's a type of naming called common names, and then there's the IUPAC names, which you saw in the latest online quizzes. If you've taken, I specify that the acronym IUPAC stands for the International Union of Pure and Applied Chemistry. That is a group of chemists, physicists, biologists who get together and develop these rules for naming compounds, because there are many, many tens of millions of organic compounds known. We cannot have a unique name for each of those. Nobody would ever be able to remember all those unique names. So we come up with a system of rules that everybody knows, and then therefore you can name and instantly look at a name and tell what the structure is. So when you get to 3 carbons long, that's propane. So an alcohol that has 3 carbons in it is going to be based on that. This is called, now you have to use a number, because the OH can either be at the end or it can be in the middle. If it's at the middle carbon, you can name it in 2 ways. The common name of this alcohol is called isopropyl alcohol. That's the same alcohol that's in rubbing alcohol. Why is it called isopropyl alcohol? Because this, when the OH is here, the carbon, the way the attachment is made is it's an isomer of propane. So that iso means it's a different structure, slightly different than propane, the straight chain. So that's the common name. There's actually a space there, so it's isopropyl space alcohol. Or the IUPAC convention generally takes the parent name of the alkane and then drops the E ending and adds OL. So all these rules I'm going through somewhat quickly are all in the chapter 14 and 15 readings. So you can go there and read a little bit more slowly about what rules I'm applying here. But now I have to put the number 2 in because the OH is at the 2nd carbon. Now if I put it at the end of the chain, now if I just drew in CH3, CH2, CH2, now there's only 2 places the OH can be in this molecule. It can either be here or here. These are the same positions. So if I put it at the end, this now has the name 1-propanol. If I just say propanol without a number, most people assume that it's this one. But that's not necessarily specific enough, because if I just say propanol, do I mean this one or do I mean this one? That's why the numbers help and are required to be totally specific about the name. So 1-propanol or 2-propanol. Sometimes this is called N-propanol. N-propanol is an acceptable name for this molecule. The N stands for normal, the straight chain alkane. You'll see that nomenclature a lot, or that symbol a lot if you look on Wikipedia, for instance. Wikipedia is a good place if you want to look at, I hope I haven't been out of the camera view here, but Wikipedia is a good place to learn about all these chemicals if you want to get some basics. And now if you get a little bit more complicated of an alcohol, for instance, here's one that has 6 carbons. So you should be comfortable in going from the line drawing to the condensed structure, or the condensed structure to the line drawing. So I'm just going to have the line drawing in a lot of these examples. So if you're not seeing what I'm talking about, stop the video and draw out these molecules in this format if that helps you. But with a little practice, this is definitely the preferred way. So if I looked at the structure, I would see that the OH is at the end, so this is a primary alcohol, and it's on the 1st carbon. Now this line here does not represent another carbon. This is just the bond that's joining this 1st carbon with the OH. So here's carbon number 1, carbon 2, 3, 4, 5, 6. You always number the chain in these alcohols, giving the OH the lowest possible number. So I wouldn't start with the 1 here, because that would give the OH the number 6. We always want to give priority to the functional group. This is sort of the parent structure. This compound is going to be named as an alcohol. The parent name is always written as the suffix at the end of the name. So I can instantly look at this and see, oh, that's an alcohol, 6 carbons long. At some positions, it's got some methyl groups. So the 1-hexanol is needed. So this is 1-hexanol, but at the 1, 2, 3 position and the 5th position of the longest chain, I have two methyl groups. So I have to name it as a di for 2-methyl. So again, commas between numbers, dashes between numbers and letters, and then I have to insert this 1 here to tell you that the OH is at the beginning of the chain. If I didn't have that 1 there, you wouldn't know where the OH is on there. It's kind of implied that it's there based on these numbers, but it's still needed to be complete. So some of these rules seem a little redundant in numbering because you can kind of imply that where that 1 would be, or that is a 1, but this is just the rules that they came up with. So we all have to follow them. If you have an alcohol that's in a ring structure, the naming is pretty similar. The OH, wherever it's attached, is called the 1 position. Now, if naming this compound, you have two choices. You can either go clockwise or counterclockwise. You would number this ring clockwise in this case, because that would give you this position here, where the methyl group is attached, the lowest number. You always want to number it to give any substituents the lowest possible number, just like we were doing in this example. So this is the 1 position, 2 position, 3 position. So at the 3rd position, there's a methyl group, and then I'm done. I can just name it, the parent molecule is cyclohexanol, 3-methyl cyclohexanol. Let's go through some more examples. Here's another one. Looks a little complicated. It isn't too bad if you just kind of look. Okay, here's my OH. Now you have to, one thing I don't think I mentioned is if the OH is not at the end, you just pick the carbon chain that's the longest chain that contains the OH. So the longest chain that contains the OH is not this one. It's not this one. It's this one. So if this is the longest chain of carbons that contains the OH, I have to number it from the end closest to the OH to give the OH the lowest number. So this is carbon 1, 2, 3, 4, 5, 6, 7, 8. At the 4th position, then, I have an ethyl group, 2 carbons. So there's 4-ethyl, and then -2 at the 2nd position is where my alcohol is. And it's an 8-carbon chain, so therefore it's based on the hydrocarbon octane. And we drop the E of octane and add an OL, 4-ethyl-2-octanol. If you want to draw that in a line drawing, you could just, easiest way to do that is to draw your longest chain horizontal. It doesn't necessarily have to make a bend in it like that if you don't want to. 1, 2, 3, 4, 5, 6, 7. It will naturally make a bend in this case because of the way these line drawings are. Here's my longest chain. I just kind of flipped this thing over to get this. And then remember, if the kink in the chain is pointing downward, there's my 1st carbon, or my 2nd carbon, sorry. The methyl, this one is drawn pointed downward, not upward. And there's carbon 1, 2, 3, 4 at the 4th position. I have that ethyl group, which I just draw as a V shape. And then here's the rest of my carbons. Now, there are many alcohols that contain more than one OH. Sometimes they contain 2 OHs. So those are named in a little different way. How do you name them? Well, let's just say you picked this as your parent name, like this is the number 1 position. How would you do that? There is no way to do it really. So you don't know which OH takes priority. So all you have to do is number the longest carbon chain to give the OH, wherever they are, the lowest numbers. So I'd number it from this direction, 1, 2, 3, 4, 5, 6. If I started from this direction, that would mean that this OH is at the 3rd position, 1, 2, 3, and this one's at the 5th position. So 2, 4 is a lower combination than 3, 5. You see these things over and over in my examples I'm giving you. But repetition is helpful in learning this stuff. So this compound is named 2,4-hexane because it's 6 carbons diol. That's a little strange. Looks a little strange, but again, just like I have to name compounds that have 2 methyl groups, like this one back here, I had to name it dimethyl. Not only tell you where the positions are, where the methyls are, but I also had to tell you that there were 2 of them. You have to do the same thing here. There are 2 alcohols, 2 OH groups, so I have to name it a diol, and I put that at the end because that's the parent name of the molecule. And I also have to tell you where they are, 2, 4, because there's many places where these 2 alcohol groups could be if I didn't specify the 2 and the 4. And believe it or not, there are actually alcohols that have 3 carbons in a row, or 3 OHs in a row. This is a very well-known and useful molecule called glycerol. Sometimes it's known also as glycerin. They actually use it to make nitroglycerin, which is an explosive, but it's also used to treat patients with heart failure. Not sure how that works, but it does. It's very effective. How would we name this compound? Well, it's called 1,2,3-propane triol for similar reasons that this is 2,4-hexane diol. You have to put the positions of the 3 alcohols, because the OH, you could have two OHs on here and none here, so that would be 1,1,3. But these, in this case, the alcohols are at the consecutive carbons. Excuse me. The 1, the 2, and the 3. It doesn't matter if I call this number 1 or this number 1. It's 1,2,3-propane because it's 3 carbons long. I don't drop the E, notice, in these names for the diol or the triol. I keep the E there. And then I just put the suffix tri for 3 alcohols with the alcohol functional group suffix OL. So this would be the IUPAC name. This would be a more formal name, I guess. This is a common name, glycerol. The word glycerol doesn't tell you that it's 3 carbons long. That's why they like using this systematic rules, this IUPAC rules, because it tells you instantly it's 3 carbons long. But glycerol is used, it's present in fats, oils, and soaps, actually. This is, we'll talk more about this later when we talk about esters, but glycerol, if you substitute one of the hydrogens, or each hydrogen, with a long-chain fatty acid, and I'll show you this later on as well, you get a molecule, a very important molecule or class of molecules called triglycerides. If you ever have blood tests done, your doctor will tell you what your triglyceride level is. It's really a measure of how much fat you have in your blood and how much cholesterol you have in your system. But you want your triglycerides to be somewhat low. But olive oil and butter and, bacon fat, any fats that we consume or even use in soaps and things have this general structure. They're based on this 3-carbon alcohol called glycerol. And these long chains of carbon that you see can be any length. They're generally even numbers varying from, 4 carbons to up to 18 carbons long. The variation of the chain lengths and whether or not they're all saturated or they have a double bond, which is called unsaturated, that will influence their boiling points and melting points, and it will influence whether or not they're solids at room temperature or liquids at room temperature. Olive oil, for instance, is a good oil, so that would be a fat or an oil that would have a lot of double bonds in it. If these were all single bonds, that's called a saturated fat, and they generally tend to be more unhealthy for you because your body doesn't really know how to break those down. Some alcohols are tertiary. That I think we've gone through a few primary and secondary. Tertiary alcohols like this are alcohols that have the OH attached to a carbon that has 3 carbons attached to it. So this is a very common tertiary alcohol. It is called T-butyl alcohol or tert-butyl alcohol. Here's some of the different names we can use for this compound. They call it T-butyl for obvious reasons. The carbons make a T shape. That's where that comes from. But it also comes from the fact that carbon here is a tertiary carbon. And we give it tertiary that symbol 3 with a degree symbol. Primary is a 1 with a degree symbol. Secondary is a 2 with a degree symbol. Tertiary is a 3 with a degree symbol. It just is telling you the structure of the carbon that contains or that's attached to the OH. So chemists like that notation because it's a quick way of denoting the geometry of a molecule. It may not mean much to you, but just again, this is just meant to give you an overview of all these different types of compounds. But it's kind of easy to remember. Then tertiary means it's bonded to 3 carbons. The number is the same. Secondary means this is bonded to 2 other carbons or the OH, etc. But the more formal name for such a compound, how would you apply the IUPAC rules? Well, you would just pick the chain that has the OH in it. That's the longest chain. So that would be this one or this one. You'd get the same answer. It doesn't matter. It's only 3 carbons long. So let's just say this is the longest chain. So at the second carbon of this chain, 1, 2, 3, there's an OH. That's why it's a 2-propanol. The longest chain is 3 carbons, so it's based on propane. So this tells me that I have the OH at this carbon, and then at that same carbon, the 2 carbon, I also have a methyl group. So I have to call it 2-methyl-2-propanol. And sometimes it's even drawn like this with a T group. So this would be my line drawing of the alcohol. It looks like a T shape. So I'll end this video here, and then I will finish up talking about aromatic alcohols, or I'll start the next video talking about aromatic alcohols.